So with the 10th birthday of threaded building blocks, we need to do a roundup of its most salient features. The first we're going to talk about are generic parallel algorithms. Okay, so this is similar to OpenMP. In OpenMP you can decorate a for loop with a pragma and have it be parallelized. Here we replace the for loop with an entire threaded building block parallel for. Okay, and when we do this, then parallelism within the for loop is enabled. Okay, so we have a code snippet below, and it's really simple. The for loop here again is replaced by the parallel for, which divides up the iterations into tasks and provides them to the library's task scheduler for parallel execution. Okay, so here you see parallel for, it will count from 0 to 1000, and where it says function, that's a function that I will create in just a minute, and it will call that function. So here's some actual code doing what I was talking about. This is the parallel for construct. I'm going to count from 0 to 1000, and I'm going to call this function. Here's my function, and I can basically do anything I need to in that function. So this whole idea of concurrent containers is very, very convenient and useful. If you use the system, say queues and stacks and other similar items, they're not thread safe. So various threads can go in there and try to use them at the same time, and it's going to have unknown results. That's because they're not thread safe. It's an invitation for disaster, basically. But threaded building blocks offers some items such as the concurrent queue, and this is thread safe, so you can call it from multiple threads and it's okay. And here's an example. I've got a concurrent queue which takes integers, name my queue, declared somewhere else, and now I'm using it. And here's a really short code example showing that. Here's my external declaration of my queue, and it's storing integers, so I'm going to use this. I attempt to pop an item, and then I can do something with that item. And this is completely thread safe. So let's talk about thread local storage next. So the TBB library provides two template classes for thread local storage. Both of these provide access to a local element per thread and create the elements on demand. But they're both different and they have different use models. The first class provides thread local storage for holding per thread sub-computations that will later be reduced to a single result. What that means is you can have maybe 4 threads that are doing different things, but at the end their computations are combined to provide a single result. It's very similar to the OpenMP reduction clause. The second template provides thread local storage that acts like a standard template library container with one element per thread. The container permits iterating over the element using the usual standard template library iteration idioms. So now let's talk about task-based programming. So the TBB library provides both a high-level and a low-level interface to its task scheduler. These interfaces can be used when no generic algorithm is provided that exactly meets your needs. The high-level interface class task group lets you easily create groups of potentially parallel tasks from functions or lambda expressions. The low-level interface class task permits more detailed control, such as control over exception, propagation, and affinity, but is not as user-friendly. So here's an example. We're counting to the nth Fibonacci number. And as you can see, it spawns 2 task groups because remember in Fibonacci, it's always going to be n minus 2, n minus 1. As I tell my computer science students, we're breaking the problem into subproblems. So here's the live code example of what I was showing you. So we're going to find the 5th Fibonacci number. It calls this function, and then this task group is going to be spawned twice, once for n minus 1 and once for n minus 2. So anytime you're working in a multi-threaded environment, synchronization primitives are essential. These are the things that allow you to make sure you're not getting data races or you're not having any kind of data locks of any kind. The main one is a mutex, mutexes and locks, and TBB provides excellent support for these. So in conclusion, the threaded building blocks technology is 10 years old. It has been a workhorse for multi-threaded applications this entire time. So the next time you're building a multi-threaded application, you should definitely consider TBB. You can't go wrong.